This conference will now be recorded.
So uh, before starting the session, I would at the start of the session, I would like to give you the list of whatever things we are going to discuss throughout these synthesis and STA sessions. And there are certain prerequisites of these synthesis and STA, like CMOS fundamentals, and then you should be aware of full PD flow, and all those things are there. So that we are going to discuss after that. So here, what are things we are going to cover? I'm going to list that out so that you have your idea. So we will be starting with synthesis flow, and we will be running synthesis. So we will be starting with synthesis flow and run the synthesis. In that, there are different optimization techniques that tool is doing. So what all optimization techniques tool is doing from inside, because some of the optimization techniques we can activate, we can also tell the tool not to do certain things. So it is uh, you can just direct the tool to honor some of the settings which you allow to which you are allowing the tool. So how to do that, and how what all optimization techniques that is happening inside, that is we are going to discuss. So synthesis optimization techniques that we are going to follow. Then, as everyone knows that we from the synthesis, from the start, in physical design, whether it is synthesis or PNR, PPA is really important. So we work towards PPA to achieve better power, better performance, and better area. So here, how to achieve power reduction techniques. So these are really important as far as physical design synthesis is concerned. So we are going to analyze power and timing reports. Analyze in the sense that always remember that power and timing, if you want to achieve power, timing will be a trade-off. If you want to achieve good timing, power will be a trade-off, right? How it happens, that we are going to see. So we will analyze the report, we will do some changes. Again, after the changes, we will again analyze the reports. So these all things we are going to do here. These things we are going to do in synthesis itself. So like I can just, so we will add how we are going to do this. We are going to add or remove certain libraries to analyze power and time. So different flavors are there: HVT, LVT, RVT. So libraries are there. We are going to change those and see that when we were using, for example, only HVT, what was the power, what was the timing? When we were we are using only LVTs, what was how the optimization happened? and are we able to see any LVTs in that, or are HVTs in that? What is the power? What is the timing in that case? And if there is certain particular pattern that we see, like only HVT or only LVT, why tool is doing that? That we are going to analyze. So we are going to again do analysis based on different voltages. So you must be knowing that there are different libraries. So libraries which are having cells, which are libraries working on 0.95. For example, we are having two libraries. One is working on 0.95, another is 0.75. So we will first give only one type of library working on only 0.95, then another one at 0.75. We by doing this, we are again going to see the power and timing, how the tool is optimizing everything. Why, if you see certain pattern, if you see certain LVTs, if you see certain RVTs, HVTs, why it should be happening. So that those analysis we are going to do. Then we are also going to in synthesis, like how do you can you do any timing fixes that we are going to do. For example, we are going to do path grouping. If you see that there is lot of timing which may be the issue there going further, so how the multi-cycle path is working, how the path grouping is working, that we are going to apply and see the reports again. So here, under the point, whatever sub points I have mentioned, we are going, you can say, in short, we are going to do full proper power and timing analysis throughout. So just give. Then we are going to see another power reduction technique that we are having. We are having multi voltage reserve. This is again the power reduction technique. So multi voltage. So what's proper theoretical explanation with proper explanation of each and every to do here on
Hello, we're not able to hear. Is everyone able to hear? No.
Am I audible? Hello.
We can hear, but the voice is low. Very
Right now, what is it? How about this now?
Now it's good. Now it's good.
No, it's good. Okay, fine. So just let me know what you just. Uh, I hope now it is clear because I think some of the issue with my headphone. Is my voice clearly audible?
Yes, now we can hear you.
Yes. Okay. So can I just can you please let me know like was I not audible from the start? Should I again explain everything from the start? Till what point or till what point you were able to?
Point 3A, we were able to hear you. Power reduction
Okay.
technique, analyze power timing report. After that, I think we lost you.
Yes. So please, if I am not audible, unmute and let me know. I may not be able to realize that I'm not audible. Fine. So I was saying that all these experimentation which you see, we are going to do it on ICC2, like synopsis tools, design compiler for synthesis, ICC2 for PNR and PrimeTime. So that is what we are going to work on. So as I told you, like we are going to run we are going to run the normal synthesis flow. We are going to go through the theoretical concepts of synthesis and then do it on lab also. We are going to run the synthesis, and after that we are going to see what all optimization techniques that is happening inside the tool. The tool is doing in this. So those are called as synthesis optimization techniques. So there are multiple like boundary optimization, retiming. So there are different concepts which are really important to know. So we are going to see all those things in synthesis optimization techniques. After that, we are going to discuss power reduction techniques. As I told you, PPA, that is what we are working towards from the start of physical design. So power reduction techniques that we are going to see. In that, we are going to analyze the power and timing report. So whatever synthesis we did here in the first go, so we are going to analyze power and timing. that what is the leakage power, what is the dynamic power, how the reports are, what is the slack that we are getting, and what all flavors of the cells that tool has used. So in that way, we will understand that, okay, so how tool has balanced in between power and timing. After that, we are going to analyze power and timing again by changing the files which we are giving in link and target libraries. So the concept of link and target libraries, right? If you are not aware of it, or and are not able to recall, obviously we are going to do that theoretically also. And then we are going to practically change those files, like for example, just giving LVT and checking, just giving HVT and checking. So here we are going to add or remove certain libraries, provide particular format of libraries, and then see timing and power, analyze it, that if we are only giving LVTs, so what, because LVTs are the ones, the cells which are really fast, but the power dissipation is more. So how the power dissipation is increasing in this case when you are just giving LVTs, and we will compare it with another experiment that we are going to do just by providing HVT cells. So we will do comparative study over here. When we gave HVT, when we gave LVTs, what was the timing, what is the timing, and what is the power dissipation that happened, leakage power and dynamic power. So that we are going to analyze properly here. Then we are going to analyze, so again, the power reduction techniques using different voltages. So we are having multi-voltage designs. So multi-voltage design we apply in physical design, we see different voltage islands are there. So how the voltages play important role as far as your power and timing is concerned. So we are again, so libraries are there. So I will just write here some libraries you will see like this. Just let me connect me. Right. So, for example, I will write the library name which we are having here. For example, I am talking about SS 0P95 50 sorry M40C, like this, something like this. So it's a slow corner working on 0.95 voltage and the temperature is -40. Like this, we are having different libraries working on 0.95, 125, plus 125 degree Celsius temperature, like that. So that we are going to analyze, we are going to give different libraries and see that how it is making changes in timing and power. So after that, we are also going to, as optimization techniques we already discussed. So one of the thing to fix the timing is power path grouping that we do in synthesis. So path grouping or multi-cycle path, these are the things which we give as a fix to achieve the timing, to reduce the slack which we see in synthesis. So path grouping also. So here in this section, we are going to do rigorous experiments to analyze timing and power. You can see. I hope I'm clear. If there is any question, you can ask me. Okay. Fine. Then next, in the next section, we are going to see UPF, because as in a power reduction technique, UPF plays really important role, because if you are having multi-voltage design, UPF will be there, and how the UPF file is written, what all important commands are there. So how the UPF, like we have to define first the port. So UPF works like this. how you write the UPF. So, for example, this is your block. So we define what? We define ports, we define nets, and then so this is, for example, this is VDD port. So this will be VDD net, and like that. So when how do we connect these two? Because tool knows that okay, some voltage is coming here. Okay, this port is getting connected to certain net, right? But it knows it, but we need to define it that okay, this voltage whatever is coming, we will be calling it as VDD. And then so like that, we have to add commands to create UPF. So if there is a multi-voltage design, there will be different commands defining different voltages also. So all those things we are going to see. So UPF, we are going to analyze, study, write the UPF, rigorous study of UPF we are going to do here in multi-voltage in this section. Then we are going to see, so there are two types of synthesis: physical aware synthesis and logical aware synthesis. So physical aware logical aware synthesis, if I am getting very first, like the synthesis team is working for the very first iteration, and we are getting all the files, RTL and all the related files, and I'm not having any layout related information. So that will be called as logic aware synthesis. And what is physical aware synthesis? That we are already done with certain iteration, or first iteration is already done. PNR people has created floor plan. So we will take that floor plan def, right? Floor plan def, what all information the floor plan def is having. It is having the information of, it is having the information of ports which are placed, core and die area. So if the information of core and die area is there, means utilization, how big is your core, like how the cells are, how the your ports are placed, how the macros are placed, what are the location of the macros. If it is a multi-voltage design, so where and how big is the voltage area that you have created. If it is different, so all this information will be there. So tool will be having better information, like layout information to some extent. So it will be doing better timing calculations in case of physical aware synthesis. So we are going to run the physical aware synthesis. We are going to, so these also theoretically we are going to learn, and we are also going to apply that practically online. So we are going to see logic aware and physical aware synthesis. So when we do it, so at last we are going to compare both the timing reports, that how, and that will come. So theoretically we say that physical aware synthesis is better as compared to logic aware synthesis. The reason being, physical aware synthesis connects with PNR in a better way, because tool is having information about location of the ports and macros, voltage area, and what is the utilization, what is the shape, size of the core, like that. So the better timing calculation is there. So that's why physical aware synthesis is better. So that we are going to analyze here. This is we are going to do. Then we are going to do MCMM discussion. Right. So theoretically, what all things are present? What is LGC? What is how MCMM? Like what role MCMM actually is having in the design, that we are going to discuss, and then we are going to write MCMM. You can say SDC. So here the main aim is to get the idea, like how to approach, how to approach if you want to create MCMM from scratch. So from scratch, if you want to create MCMM, how will you approach it? What all things you will see? What are the scenarios you will see? And then you will apply the commands. So these things. So we are going to write MCMM. So in this lab, we are going to do. Fine. After that, there are again very important and little bit tricky concepts are there, like multi-cycle path. So we are also, so after writing this, we are going to again do the timing analysis. We'll write it in this way. We are again going to do timing analysis, and we are going to timing analysis and application of multi-cycle path. So how application of multi-cycle path is changing the timings when you are working. So this is what we are going to do here. We are going to apply, before applying the multi-cycle path, we'll see the timing. After applying multi-cycle path, we'll see the timing, and we'll do the comparative study. Yes, so we are, after that, we are going to discuss about how clock gating, how to handle clock gating, what all, so clock gating. So when a tool is having clock gating, it is not easy for the timing analysis, because tool becomes prone to have the timing violations, right? So how, what is clock gating? What all what do we achieve if we do clock gating, and how to handle clock gating, as well as well as handling asynchronous design. This we are going to discuss. If the clocks are asynchronous, so synchronizers are required. The RTL team has to add that. So whenever we are, it is also, we are going to discuss that we very normally we say adding a multi-cycle path or adding a like synchronizer in between. But when we are doing that, it's not easily happening. The RTL team has to add that. So that's why all these things has to be very mindfully done. So all these things we are going to discuss how to handle it. Then after that, so here mostly these things we are MCM, from MCMM we are going to do it on like multi-voltage design that we are having on cutoff, and then so we are going to do timing analysis on different stages of PNR. So we are going to do timing analysis on different stages of PNR, like placement stage. Placement stage, if you are having timing, timing is violated, so you have to add path grouping, magnet placement, bound creation. You cannot add buffers or inverters at this point. You can do it, but it is not preferable, right? So all these things. So when you are having a timing violation in a placement stage, how to fix it? What will you do to fix it? So those all things we are going to discuss. Then at CTS stage, timing analysis at CTS stage that we are going to do. And after that, ultimately, we are going to do timing analysis on PrimeTime. So these are the topics that we are going to discuss throughout the sessions. So before I switch to prerequisites and give you the idea about what all things you should be knowing, if there is any question, you can ask me. Screen is not visible. Is it happening for everyone? Is it happening for everyone?
No. Screen is visible for me.
Okay. Snehita. Okay, I will just reshare it. Is it visible now to everyone?
Yes.
Okay. Right. Yeah, please unmute. Actually, I'm not checking the, there is no pop-up for the messages. So you can just unmute and let me know if there is any issue. Because LAN is not working. Yesterday's, this, just LAN is working. LAN is working. Is it working for you? No, it's not working. We're using Wi-Fi. No, it is also not working. We'll see. Okay, thank you. Fine. Then we'll just move ahead with the prerequisites. Just give me a minute before that. I will add some more points here. I've missed some points that we are going to do. So here with CTS, we are also obviously here prime time is also we are going to do after routing, but still I will mention routing stage. So there are certain questions that why the violations increases greatly from CTS to routing. Is there any difference in global and detail routing? That because till before routing we were doing timing analysis on global routing, and when the detailed routing happened, what was the timing? The difference in the timing, and then we are also going to discuss about effects of crosstalk. Effects of crosstalk. We are going to do proper study on crosstalk, how the what is the victim, what is the aggressor, and what are the fixes of crosstalk. And we are also going to discuss about CPPR. Right. So yeah, crosstalk, all the fixes and all we are going to do. Yes, we are also going to discuss about in the prime time how to. Just give me a minute, if I'm doing this. Yeah. So we are going to do crosstalk analysis and fixing using prime time. So whatever crosstalk analysis, effects of crosstalk, it's analysis and fixing. Whatever fixing is feasible using prime time that we are going to see. So these are certain points that I missed. So we are going to also discuss about this in detail. Fixes. Exposed. So useful skew methods and this, yes, there is a useful skew method that we are going to discuss. tuning the clock, using the tuning the clock in like changing the clock, adding the buffers. Are you expecting that? But yes, we are going to discuss about useful skew method, analyzing, adding the buffers and all like that. Right. Yes, fine. So now we will just again, I'll take 2 minutes of this. I'm getting a call from management. Just give me 2 minutes. Yeah. So now to get all these to get hold on STA synthesis, we should know prerequisites. So this is the advanced course. So certain things are expected from you, like knowing CMOS circuit, right? So this is like certain things why CMOS is important to know, because CMOS FinFET is being used for IC fabrication. And when we talk about power, so we give the power fixes, we do everything, but we should know from where that power is coming from, right? So that is why knowing these is highly appreciated. So I will be discussing it here today. So how the very first thing is CMOS circuits, the working of CMOS. I hope inverter circuit everyone knows. How does it work? Can anyone just give me the idea? How does this CMOS inverter works? Okay. So CMOS So CMOS, this is what, this is NMOS, this is PMOS, right? Write it. This is NMOS, this is PMOS, and this is VDD. This is VSS. This is load capacitance CL. So this is CMOS inverter. So inverter, when we are giving, zero, what is happening? Zero. When we are giving zero, your NMOS is working. Yes.
Madam, that is the PMOS and NMOS you reversed it, madam.
Sorry. Yes. So when we are giving zero, so your PMOS is working, your NMOS is off. NMOS is off. So your load capacitance CL is getting charged. So it is charged and it's giving us 1. And when you are giving 1, your PMOS is off and your NMOS is on. So your load capacitance CL is getting discharged from NMOS through VSS, so to the ground. So it's giving you 0, right? So this is how it is working. We also have this V out versus V in characteristic, which looks something like this. And it is divided into different parts like A, B, these are the C, D, and E, like that, different regions. So this one. So we have been taught that how the working goes on to like how when you are providing. So this is 0 when V in is is switching from 0, and you're switching from 0 to 1. So VDD. 1 is nothing but full VDD. What happens at the V out? So when it is 0, it's giving you full 1. And when it is switching, so during the switching, what is happening? PMOS and NMOS, whether they are, just. Okay. So PMOS and NMOS with PMOS and NMOS, whether which one is on, which one is off at which point of time, right? So here we should be knowing what is happening. And then the most important right now I'm going to touch is region C, right? So this is the region, this much is the region where when the switching is happening at region C, which is just in between 0 and 1, your both PMOS and NMOS are in saturation region. And when both are in saturation region, means both are on. That means direct current is flowing from VDD to VSS. At this point, high amount of power is dissipated. So this is called as switching power. So when the switching is happening 0 to 1, 1 to 0, so this is the part of dynamic power. So when both are in saturation, both your PMOS and NMOS, direct current is flowing. For that one, at that particular instance, high power dissipation happens. So what we want? We want the C to pass as soon as possible. That means we always draw our signals to be like this. Correct. But we know that this is the ideal case. This is not a practical case. Our signals are like this, little bit transition delays there. It will be there. That's the practical thing, right? So when your signal is transitioning from 0 to 1 or 1 to 0, we want this transition to be as soon as possible. Means we want this to be approximately ideal. Correct. So that is what. Yeah. Okay. That is why we want. So when it is the transition is less, we will be having this switching very less for very less amount of time. PNN will the PMOS and NMOS will be in saturation region. Less amount of power will be dissipated. Right. That's when we will understand that okay. That's why we are checking the. So there is a constraints that report constraints max tran that we do. If you're already working on, or if you have done PNR, you must be knowing that max tran we check and we fix it. Right? What is the reason that we fix it? For one of the reason is this: if more transition delay is there, more power will be dissipated. Another some more reasons are there, like one of the second reason is if the transition is more, for example, if the transition is like this, transition is more, draw exaggerated, so your on time will be less, so it may lead to pulse width violation. That's why transition we want to be less to be better. This is also one of the reason to fix the max transition. But when we are talking about max, why? So we should be knowing this, right? So that's why transition is really important. That's why we are checking it, we are fixing it also. Okay. Now again, there are certain things. For example, there are your transition depends on, this is the ID equation is really important to know. So ID is equals to half mu n C ox W by L V G S minus V T H whole square. So these are certain components that so in this equation, knowing this equation, understanding this is really important to understand, to control the transition delay which is happening. So at this point, I want to just show you one this table. I'll just copy the table. Just give me a minute for that. So these are the factors that we should be knowing that affects the transition, and transition also affects setup. That when we are doing the timing reports and all, we will understand that, right? So these are the factors. These are the factors: load, capacitance, input, transition, W by L ratio. These are the these 3-4 factors. 1 2 3 4 factors are obviously dependent on ID equation. You can analyze it. Let's talk about load capacitance. How do we know what is the effect of load capacitance? So for example, I'm again drawing it quickly. Right, load capacitance. For example, I am providing one fixed VDD here. So for just consider that the VDD I am providing is 1 volt. Just consider it, and it is having some ID, we are having it here. Okay, so now what is happening right now? The value of load capacitance CL is some 0.5 Fermi-Farad, right? Now with the same ID and same VDD and same ID, so there is some time it required to charge this capacitance of 0.5 Fermi-Farad. But now if I am increasing, now what I will do, I will increase load capacitance CL from 0.5 to 1 Fermi-Farad. So what will happen? ID is same. So right now ID will require more amount of time to charge this load capacitance CL. Right. So that means if the load at the output is changing, if it is increasing, your ID will take more time to charge that load capacitance CL. So your transition will increase. Means when the load capacitance takes time to charge, that means transition is more. If the transition is less, means load capacitance is taking less time to charge it, like this. This will be more transition, this will be less transition. So if I am increasing load capacity, so here, why it is important to know this? Because we have the concept of fan out, right? We have the concept of fan out. So, so for example, this is some cell. Just this is some cell, right? The output capacitance of this cell is nothing but if I am connecting this to some different cells. 1, 2, 3, 4, 5, like this, right? Just random cells I am drawing. Correct. So the output capacitance, this CL which I drew, is nothing but the input capacitance of whatever is at the output. Whatever is at the fan out, right? So if this load capacitance is having certain value which of CL, which it is able to properly charge within its limit. But if that fan out, if that CL increases, so it will take more time. Your transition may get violated. So knowing this is important, that how CL. So if I'm increasing the load, how I'm getting the more transition, right? Then I am giving more drive strength cell to fix that. How it is happening? Though we are giving the fixes, but how fundamentally, what is the fundamental between them? What is happening behind that? That is, you should be knowing, and you will be knowing it by knowing CMOS. So here, so when I increase the load capacitance CL, your transition increases. So increase load capacitance, your transition, output transition means delay. It's nothing but delay. I will write it here. It's nothing but delay. So if I increase the load capacitance, the transition will increase. If I decrease it, the transition will decrease, means delay will decrease. Input transition. Now, let's talk about input. Allow me to just read. Now input transition. So if there is a cell, some cell is there, and gate or gate, any cell. So there is input transition and output load. This is how you calculate the delay. Now you are giving input only delayed. So there is nothing in the cell which is making it better, right? The output will be delayed only. Simple logic. So that's why when you increase the input transition, the output transition also increases, and vice versa. When you decrease it, it will also decrease. So these are the two factors which is not there in this equation. Now coming to this equation, so you can see now when I increase the load increase the W by L ratio, width by length. So W by L ratio, it is, you can see from the equation, it is directly proportional to ID. Now one more thing, now ID, so ID is more, if it is strong, it will be charging the load capacitance CL faster. If the ID is slow, It will be charging the, so it is like if I provide less VDD, it is directly proportional to ID. ID will be less. It is directly, if ID will be less, the delay will be more. It is inversely proportional to the delay. So if I increase the VDD, earlier I was providing 0.5 volt, now I am providing 1 volt, right? So my ID will increase. When my ID is increasing, my delay will decrease. This is what is important to understand. So, so I will write it here in this way. So here, now W by L ratio. So W by L ratio, if I'm increasing the W by L ratio, it is directly proportional to ID. So ID will increase. When the ID will increase, the delay will decrease. Correct? Say, if I decrease the W by L ratio, the delay will increase because ID is decreasing. Same goes with like now VDD. So as I've already, I guess, told you about this. So if we are providing VDD, more VDD, VDD is directly proportional to ID. ID will also be more. Correct? When ID is more, it is inversely proportional to the delay. And then comes the mobility. Mobility of charge particles. So it is mu n with respect to NMOS. It can be mu p with respect to PMOS. So sometimes you will also see mu x, either you consider NMOS or PMOS, like that. So again, the mobility is directly proportional to ID. So it has this, if ID is increasing, mobility will be increasing, the delay will be decreasing, or mobility if in vice versa. If I increase the mobility, ID will be increasing, the delay will be decreasing. If I decrease the mobility, ID will decrease, the delay will increase. Now next is VTH. That is threshold voltage. Threshold voltage is the minimum required voltage to turn on any component. So threshold voltage. So here the threshold voltage is getting subtracted from VGS. So if I increase this threshold voltage, right, what will happen to my ID? Because more amount of values getting subtracted from VGS, so my ID will decrease. So here threshold voltage VTH is inversely proportional to ID. So if I increase VTH, my ID decreases and current will and the delay will increase. ID decrease, delay will increase. So that is very clear. If I increase the VTH, output transition increases. If I decrease the VTH, output transition decreases. Fine. Yes, temperature. Right now, I'm just Sachin. I'm just giving the yeah, clear picture, like the whole picture of what we are going to do here. We will slowly move to that, and yes, going ahead when we are I will be explaining triple MC. I'll be explaining temperature inversion also. That you are going to do going along the course. We are definitely going to do that, but right now I'm just going to go through the prerequisites that I talk about. Okay. Fine. So that is also all these things are important when we are talking about cell delay. When we are talking about cell delay. Cell delay, if there is any cell, if there is any cell, you should be knowing its input transition and output load CL. That's how you will calculate. So how tool is calculating cell delay? So the cell delay, these information are present in .lib files. We are also going to, so here I may have missed this also. So we are also going to, when we are doing synthesis flow, we are also going to go through like what all things present. So input files are there present, right? So what all things are, what are the contents of input files that we are also going to see. So what things are present in which file? So .lib file is having the lookup tables. So we are going to see that how the lookup tables are arranged, how you can also calculate some delay, how it is arranged, how to understand that we are going to see. So cell delay. So that is how now by knowing all these things, you should be now knowing that how the cell delay, input transition, output load, that is affecting your transition, that is affecting the delays. If my say this is some cell, if this cell is, for example, this cell is connected to only two loads, some other cells are, only two cells are connected to this cell, same cell is connected to four loads, right? Though the cell functionality, the flavor, the drive strength, everything is same for this cell. So for example, this cell is some cross 4, that's the drive strength, and it is HPT type of cell. Same cell having cross 4 drive strength and HPT type of cell. But case 1 which I drew, case 1 and case 2, in both the cases, the delay will come out to be different. The reason being what is a fan out? The reason being what is the at the load is present. Fine. So this is what cell delay we should be knowing by this. Next is, as we are, any question will take. Yes, Shubham. VDD is not there in ID equation, but we should be knowing that if you provide less VDD, the ID will be less. Or ID is directly proportional to VDD. So if you are providing, if I compare 1 volt, if I am giving 1 volt, the ID will be different as compared to if I am giving 0.5 volt. So that's when that logic you need to apply over there. So though it is not there in ID equation, still this is the logic. So if I increase, so that is what is happening when you are giving different in multi-voltage design. I drew it somewhere. No, I guess I deleted it. So when you are using multi-voltage design, we have to give that particular library. So as I told you, we are having a library which is working on 0.95. We are having a library which is working on 0.75. So what are these? These are nothing but VDD that we are providing. We are reducing VDD from 0.95 to 0.75. ID is changing. That's when the delay is also changing in both the cases. And in both the libraries, all the cells are present. AND gate or same set of cells are present. So next is So now we can discuss about the power, as we are also working on power. So power and seams. Correct. So there are two types of power: leakage, so dynamic power, and leakage power. So different powers we are going to discuss now. Just give me 2 minutes. I'll fill my water bottle and come back.
Hello. Hello, madam. You are in the mute if you're speaking, means.
Yes, yes, yes. Wait, I'll just
Okay,
give
okay.
me. Yes. So now we will be discussing about power in CMOS. So basically, this when we say that while discharging and charging of the load capacitance CL, so this is VDD, while discharging and charging of this load capacitance, so we talk about power dissipation, right? Power dissipation. So power dissipation, there are two types in that also. So we talked overall. So this is also one thing to note, that there are different like dynamic power. Inside the dynamic power, there is a short circuit power, leakage power. These are the three: dynamic power, short circuit, leakage power. These are the power that we talk about in PD. So when we are talking in PD about the power dissipation, we are talking about all these three powers. So there is including, so there is dynamic power included with short circuit also and leakage also. So these three whole power we are talking about there in physical design. Trying to reduce all of them at once. So when we talk about this power dissipation, what happens when zero is provided, right? So here the CL is getting charged. So at this time, actually power is consumed. Right, and when the CL is getting discharged, at this time the power is dissipated. It's going to ground, getting dissipated to ground. So when we are talking about power dissipation, we are also talking about both how much power is getting consumed. We are providing battery, we are providing power supply, right? So power is consumed, and that is why it is dissipated also. So when we say that it is consuming more power, power dissipation is more, we are talking about more. Obviously, it's consuming more, it is dissipating also more, like that. So just to give you this idea that what is happening and when the charging and discharging is happening. Okay, so so dynamic power, when we say dynamic power, that is dissipated. The dynamic power is when the switching from 0 to 1 or 1 to 0 is happening in your CMOS. So dynamic power is the power which is required to charge and discharge load capacitance when transistor is switching. This is nothing but switching activities. That's why to get proper power dissipation, we require safe file, SAIF, switching activity file. So if you are having that, you will be having proper power dissipation report. Yeah. So what is, so one cycle involves fine. Okay, so what is dynamic power? It has the, what is the dynamic power? So dynamic power, so I'll go to this. It is alpha frequency, that is switching, CL VDD square. So this is dynamic power, right? So dynamic power, so alpha is a switching factor, right? F is the frequency, CL and VDD square. And what is circuit power? What is short circuit power? So again, for short circuit, PSC, short circuit power, the equation is VDD I. So I at the and P when it is switching from 0 to 1, and when it is switching to 0. Right here, I have told you switching from 0 to 1 and 1 to 0 is a different thing. So when it is switching, when the output is switching from 0 to, when the output is switching from 0 to 1, it is consuming power. When the output is switching from 1 to 0, it is dissipating the power. Right. So let me explain that how the leakage power. So there are two. Leakage power can be many many type of leakage power that can be present, but there are leakage power consumption. So there can be many type of leakage power that can be present, but the important to us is subthreshold, which is playing vital role, and out of all of many of them, these two are more significant. So subthreshold leakage. And gate oxide leakage. Correct. So what is subthreshold? So subthreshold is something. So let me quickly draw this. Right. So this is. Sorry, I will draw it a little bit. I'll just draw this. So this is what? This is source. This is what? This is drain. Very exaggerated. I draw material. This is better. Source, drain, polysilicon and side. And this is side SiO2. This is gate. This is drain. This is source, which is. Oh, let me draw it. This is source. This is drain. Correct. Now, what is happening? What is subthreshold leakage current? So, subthreshold, for example, my threshold voltage is 0.3 volt. For example, it is 0.3 volt. But what happens at 0. Somewhere at around 0.270 or 0.28, 0.29? Still the voltage has to be reached at 0.3. Still, some of the electrons from the source side will get attracted towards the positive gate, and it will flow ID current below the threshold voltage. When the threshold voltage is just about to reach, this is called as subthreshold leakage current, and the power dissipated because of that is called as subthreshold leakage power. So this is also a type of leakage power, which is flowing because of leakage current, right? So here I may give you, so okay, first, so this is the leakage power, one type of leakage power. Then what is gate oxide leakage power? So when we have already discussed about it, so when the switching is happening, right, at point C, here at point C, this one, I'm talking about this, at point C, when both PMOS and NMOS are in saturation, so what happens? Direct current is flowing from VDD to VSS. Okay, I'm sorry. This is not, I'm sorry, my bad. I want to explain about something else. Yeah, now next is this. So now what happens? So for example, right now, I will just remove these things. So what happens right now, say, consider the gate is provided with some significant voltage, right? Your source, I'm talking about NMOS. Right now, I'm talking about NMOS, right? Your source is grounded, correct? And gate is provided with significant voltage of say 1 volt. Just consider. And drain is yet to be provided with some voltage, or the drain is yet to achieve that voltage which has to be provided at it, right? It's somewhere around 0. It's increasing right now, and it has to achieve whatever, somewhere around 0.1. It's increasing, and it has to achieve that. So it may be very nanosecond time, but in nanosecond time, what is happening? Because the gate is positive, the electrons present towards source and towards the drain, they will get attracted towards the positive gate. And when they get attracted towards the positive gate, the current will be flowing from gate to source and gate to drain. It may be for very nanosecond time period, till this VD is achieving whatever. For example, VD also has to be provided with 0.8 volt. But somewhere when it is not, it has not achieved that 0.8, somewhere when it is at around 0 and still increasing, at that instance, these electrons present towards the source and towards the drain get attracted towards a gate, and leakage current will flow from gate to source and gate to drain. These are called as gate oxide leakage currents. So now I may write the leakage power equation. So I leakage. I will just write I leak. Right. These are the leakage currents which I showed. One is subthreshold leakage current, another is gate oxide leakage current. So into VDD. So it may be approximately equal to I subthreshold leakage current plus I gate leakage current into VDD. These are the leakage current. So your CMOS is really important. So the biasing of the CMOS is really important. So when the biasing is proper, it works properly. It's noise. This is like the input. Because input the input. This is the current is not flowing at the input. Proper output you are getting, because high input impedance is high. So this is the, it's not getting, yeah. So this is the leakage power consumption. Right now, next is that we work towards is short circuit power consumption. This is where, so short circuit. Short circuit power consumption. So short circuit power consumption, when again, so this is what, so we have already discussed. So when NMOS and PMOS are in, both are in saturation, that direct current is nothing but the short circuit current. Right. So this is what is short circuit current, and the power that is dissipated because of this current is called as short circuit power. Now, so main factor is, now again we should know about the dynamic power dissipation, dynamic power consumption, right? The power dissipation occurs when output is switching, and the power is dissipated due to charging and discharging of CL. This is what is dynamic power dissipation that we have discussed, right? So when the load capacitance is charging and when the load capacitance is discharging. So switching activity. So P, here I provided P. Yeah, this P. So this is nothing but the probability for 0 to 1 switch of the output, probability of 1 to 0 switch of the output. This is nothing. So here I will, okay, PTD square. This is this short circuit code. Okay, I did not write it. So I will write it here. So P dynamic is equals to load capacitance CL into VDD square into P 0 to 1 or 1 to 0. So 0 to 1 is more power affected. So this is the probability of 0 to 1 switch of the output. This is clock frequency. So here this can be written as when, like, so it is actually dependent on how much is the switching happening, 0 to 1 or 1 to 0. 0 to 1 is more important, that because it is having more dynamic power consumption. Right. So this factor, so switching activity is important as far as dynamic power consumption is required. So that is why SAF file is needed. So whenever you are having power calculations, we require SAF file also, right? So in short, we should be knowing that where does the power goes in CMOS? I can, in layman language, I can just say, where does the power goes in CMOS? Where does it go? So first is it goes in dynamic power consumption. So which is happening because of charging and discharging of capacity. Then short circuit currents. So switch. Next is leakage. So it is leaking diodes and transistors. So even when you are not providing any power supply, so when any still due to some temperature change or something like that, your component is working. That is when and the current is flowing, any current due to that. So that is called as leakage current, and the power which is dissipated because of that is called as leakage power. So these are the prerequisites of CMOS that we should be knowing, right? Because these are highly important because we are fixing all these things in PD. We should be knowing from where it is coming, why we are doing it. Fine. So now next is what I am going to give you the gist of what is synthesis, what is physical design, gist of it. Just because that is also the prerequisite. You should be knowing the physical design flow and synthesis, right? So gist of it, and then in the regular classes, obviously everything is going to be in detail. So before that, I'll take a break for 10 minutes. You also take break for 10 minutes. It's almost 11:10. We will be starting at 11:20. Yes, so we'll start again. Okay, so out of all this, so when we know the basics of CMOS and everything is fine. Now coming back to physical design, synthesis and physical design. So what is the structure that your foundry understands, right? The foundry does not understand any logic. It does not understand any RTL code. What it understand is layout of CMOS. And when I say layout, what is layout of CMOS? Layout of CMOS is nothing but what you see from the above, right? And these layout is given by the layout team. So we just take all the cells and we implement them, we connect them, and all those things are done by physical design people, right? So when I say the layout, what foundry understands, so this is something like this is NWell, right? This is VDD here. So polysilicon where gate is present here, VSS, here VSS, is so this is all the connection is also like this, I think. So this is nothing but source. It's getting connected here with VDD like this. This is nothing but, so here also, here also the source. This is NWell. This is what NWell. But you can say full PMOS. This is PMOS. This is nothing but NMOS. Right here again, the source of NMOS that's connected to VSS like this. Your poly is there. So this is the VSS here. This is the gate. Here somewhere it is the gate. So gate of PMOS and MOS here. So gate comes like this. What is the output? The output is like this here, connected to the drain. This side is nothing but the drain. Right. From here the V out is there. V out. So this is what is understandable by your foundry. When you give this to your foundry, then only it will understand that, okay, this is, and so we take this. This is given by the layout team. They will characterize these the individual cells. They will give it to us. That is what all information is present in our input files, right? And those input files are and those input files and all the information, all the libraries we use, we take the cells, we connect them, we connect the signal, we connect the clock, we connect the power, and we make sure that it is working in whatever is the given frequency, and then we give it that file, that GDS2 file, to the foundry, right? So what is the, so as I told you that the foundry does not understand the logic. It does not understand the RTL, right? So, but RTL is also, RTL being really important part of VLSI, right? Here, all the logic, behavioral logic, everything you will find here, right? So, when RTL is coming, what are the like RTL? What are the next steps that we are doing? We are doing synthesis. We are doing AFT. Right? These are nothing but gate level. Gate level. When I say it is a gate level, I mean to say that it is technology dependent. So these are gate level. Now, and now in after synthesis, everything is like it's present depending on what technology you are using. You are going to see all the, so in RTL you may see, so okay, tell me, what RTL is happening having? Can you tell me what is RTL code is having? the VHDL code, what all things it is having? Why we cannot use RTL directly in our physical design?
Only logical gates are present, no physical gates are present.
Okay. What if I would say that the behavior is present in the RTL, right? For example, there's a mux. For example, RTL is having the module called as mux. RTL having module called as mux. So A and B is the okay. So A and B is the input, and there is one select line S, and this is the output. Correct. So that inside that module, the how the mux is behaving, that the functionality of mux is actually programmed. That when S is equals to 1, so it is like when S is equals to 1, A should be provided at the output. And when S is equals to 0, B should be provided, S is equals to 0, A should be provided at the output. When S is equals to 1, B should be provided at the output. B should be provided at the output. Right? So this is the behavior of mux will be there in the RTL. Your tools, your physical design tools are not able to understand all these things. They will understand when they will find the tool will understand if it is something like this mux underscore HVT, something like this is there. This is nothing but gate level netlist. It is not going to understand that what is the behavior of that inside it. So that is what we are changing this behavioral code into the gate level netlist. That is what is happening in synthesis. Right? After that, we move to what? Physical level. Right? Physical level is nothing but here comes physical design. Right? In physical design, then we are doing multiple steps to convert that now gate level netlist till synthesis. So though behave it, so in synthesis, after you convert the RTL into synthesized netlist, they are in synthesized netlist, you will not find any behavioral structure of any component. You will directly find the names. You will find name of AND gate, OR gate, NOR gate, and so on. Marks, T marks, and so on, whatever it is. Right? You will not find behavioral. But in synthesis also, everything is logical. Right now, the tool is not having the layout information still with it. Right? It has just converted that RTL into gate level netlist, means the technology independent to technology dependent, and now we will be in the physical design, people will be converting those everything which is logical into the layout. Right? So here we are having different steps called as partitioning, then floor planning, then placement, then CTS, then routing, and then sign off. Testing, CTS routing, and sign off checks. right? So here we are now doing each and everything, like first creating partitioning means converting a big design into different partition and then giving it to different teams so that every team is working on their block parallelly. That will save time and money, right? So that is the partitioning, because the big design lakhs of cells cannot be handled at the same time. It will be really difficult and time consuming to fix the timing issues and other issues like crosstalk and at the sign off, right? So that's why they are dividing the big design into smaller design and giving it to individual different teams, and all the teams are working on their design, and then at the end the chiptop will take all the blocks and they will connect them to PNR again, and they will just release it. So that's partitioning. And then floor plan, where actually the shape, size, utilization, placement of macro is done, placement of ports are done. If multi-voltage design, voltage areas are created, that's floor plan. Then placement, all the standard cells are placed in the placement stage. Lot of optimization is done to achieve the timing and proper congestion, means to reduce the congestion. After that, CTS, that makes sure that the clock is provided to all the sequential element and with no or negligible timing issues. Then so here again we need to take care of, because CTS clock is most switching signal, so that is why it is prone to have the signal integrity issues like crosstalk and all. So from here we check now setup as well as hold as well as the DRVs as well as the signal integrity issues and fix it. Then routing also, same things we check and we do the same checks and fix the issues if there are any. Right. So, okay. We are at, so I can just, I will take session till 12:10. I have the time to discuss about synthesis. So what is synthesis? Can anybody give me the idea about synthesis?
Hi. So it is basically converting the behavioral code we have, VHDL or Verilog, to get level netlist so that we can carry forward in the PL stage.
Yes, correct. So that's the main that's the main aim to do synthesis on a design, right? Synthesis, it is a process to convert RTL code into gate level netlist, right? Now RTL code is, so we can say RTL code is technology dependent, technology independent, and gate level netlist is technology dependent, right? So this is the main aim of synthesis. Along with that, synthesis also does multiple things. Like here we can also do clock gating, right? Here DFT insertion is also done, right? Here optimization happens, right? And towards the end, we have to make sure that the LEC is achieved, means whatever was the RTL, same functionality is present in synthesized netlist, right? So what is DFT insertion? So DFT insertion is basically the DFT people will give us the scan chains. So scan chain will enable us to check the design even after fabrication. So that is what DFT insertion and optimization also happens during the synthesis. So all this, so the first point is the main aim of synthesis, and it also does these some other things also. Right now, what are the inputs required for synthesis? Can you tell me?
Yeah, so first we'll refer the RTL code. Then we need libraries, both like physical library and logical library. If you're doing the physical level, we need the physical library also. Then the text files, and mainly these are the like inputs.
Yes. Yes. So I will start with the necessary inputs. So code, RTL code, RTL code, the RTL is required. Then I will just write RTL is required. Then logical library is required. So like logical library, when I talk about logical library, I mean to say .lib, correct? RTL code, logical library, and then technology file, .tf. These are the input files, necessary input files required for synthesis. You cannot do synthesis if any one of these three is missing. It will just throw you out, right? So these, but if your design is multi-voltage design, UPF is also required. You can also give UPF. If your design or an SDC, timing constraints. Timing constraints are also there. We write SDC. We can also provide SDC, right? SDC is not one of the necessary inputs, because if SDC is not there, the tool will take necessary some by default values or necessary information if it is present from the input files, like .lib file we are already providing. So delays and all tool will take from there if SDC is not provided. But if you provide SDC, the timing calculation will be perfect. Right, so UPF, SDC, then yeah, so you also have the ScanDef. So these are the input files required for, I will just write logic aware synthesis. Right, now what about physical aware synthesis then?
There we need
Earlier
the
I
def
mentioned,
actually.
yes, floor plan def. So like earlier I mentioned, I've mentioned. So floor plan def. Floor plan is having information about core and die area, where ports are placed, where macros are placed, and where the voltage area is created. Right. So we will require floor plan def. This is having the layout information. Now, as the layout has come into picture, also the physical library will require. What is physical library? .left. Right? So we also then require TLUP. Right? So TLUP, we know. So do you have the idea what is TLUP? Anyone? Why TLUP is also required in physical aware synthesis?
For better estimation of the timing delays, like the parasitic values and all.
Yes, true. because physical aware, when the physical aware synthesis is coming, that means floor plan def is coming, that means the layout information is coming, the locations of cells of macros and codes are coming. So tool will require tool is having now the actual information of location, so it will require RC parasitics which is present in TLUT. Right. So this concept of delay calculation we must be knowing that the delay calculation in synthesis stage happens using what? Wire load model, WLM. Right. WLM model use fan out method. Means depending on fan out, it calculates the delay. Because in synthesis, particularly in logic aware synthesis, there is no layout information that what is the location from where to where. So if one this is our block. If the macro is present here and if the port is present here, how the connection is happening like this. This information is not there in logic aware synthesis. That's why, but still the delay has to be calculated, right? Because rather than having nothing, something is important, something is better. That's why we are having WLM models. It's present in your .lib files. So it uses fan out method to calculate the delay. Right. So during synthesis, we are using WLM, the tool is using WLM model to calculate the delay. During synthesis, WLM model is used to calculate the delay. But as soon as physical aware synthesis, as soon as tool is now having some layout information, it will require TLU plus file. What TLU plus file is having? It is having RC parasitic information per unit length of layer. So parasitic information, that's how the now tool is actually calculating the delays. Right. So we are going to see this input files. We are going to open it and see the WLM models and how it works and all those things. So these are the inputs to synthesis. Correct. Fine. So now after this, so there are different steps also in synthesis. So mainly we talk about analyze, elaborate, and compile. After that, we get the output. But in analyze, what happens? In elaborate, there are multiple things that is happening at elaborate. In compile, what all things happens? That also we are going to see in detail. That what all things are happening in elaborate. Many things are happening under elaborate stage. Right? And compile. And throughout, when these are happening, what are the some optimization techniques that is being followed by the tool? What are those? Those are also we are going to discuss. Right. So these are the steps. When after these steps, the output is generated. Right. So we can do certain checks. We can do certain checks like timing, setup check, cap, RAN violation, power report also we can check. Right. So these are the things that we are going to do in synthesis. Right. We are going to discuss about it in detail. Fine. Let's discuss about what is, like I asked, and then yeah. What is scan chain? What is DFT? I've told you that testing chip after fabrication. Post silicon validation is possible because of insertion of the scan chain. Scan chains will enable us to even check the design after the fabrication. That's called as post silicon validation. Right. So do you know about scan chains? does it affect our functionality? What happens with, like, what do we do with scan chain? Is there any difficulty that we can face because of scan chains?
Will be done in placement stage. Scan chain reordering.
Yes, that is also done there. We can also add scan chains in synthesis, and if we are not doing that in synthesis, we will do that in PN. And scan chain reordering is happening, yes, to achieve the time, because if the scan chain is not properly reordered, or it may affect the timing. Yes, that is what is happening. So I will just we are talking about DFT, design for testability. Right. So testing the chip is called testing the chip after fabrication is called as post silicon validation. So post silicon validation, it is possible because we are adding the scan chains, right? So where these scan chains are coming from? So DFT team is going to give us these scan chains. They will modify the, so it may be present in netlist also. It may be present as a different input also, like scan depth that I mentioned earlier. This, right? So DFT team will modify the netlist without affecting the functionality. So that chip is tested after fabrication. Right? So what we are unable to do it. So we do what? Scan chain insertion. It can happen in synthesis or in PNR, anything, right? So what it enables us? It enables us to have a built-in self-test, right? And it is basically an automatic test pattern generation. So basically how it looks like. So normally we are having D flip-flops like this. Normally we are having D flip-flops like this. D, so it is having D, Q, clock. Right. And when scan chain, we are talking about scan chain. So these flip-flops will get converted into scan chains like this. So there will be additional pins that you will be able to see in the flip-flops. So they will be connected like this. Now D will be there, Q will be there, scan input, scan enable, clock, Q bar. Additional pins will be there. So here the combo cells will be there. Our normal D flip-flop will get converted like this. This will also happen, or additional chains will also be there. D, Q. Again, these are our normal functional, this D, Q, right? So when it is working in, so again, it is having scan input, scan enable, clock. It is having scan input, scan enable, clock. So when it is working in func mode, this will work. When it is working in test mode, this will work. Scan input will work. So to make the scan input, so here scan input is having certain inputs. The D is going to have some other input, right? There is one scan enable pin here. That will enable the flip-flop, whether it is working in func mode or test mode, right? So if mode is equals to 1, work in func mode. Mode is equals to 0, work in test mode. So this also we are going to see when we are creating triple MC. So we are going to see the concept of modes, right? So when we are adding DFT, so we will be having two modes, func and test. So how this, because clock is also given, so different clocks, test is having different clock, right? So it will be having the clocks like this. So this is functional clock, this is test clock, correct? Like this. Right. So what constraints are we going to provide so that your design works in test mode? What constraints are we going to provide so that your design works in like different modes, func or test, whatever. Right. So this is what, so normally, so when I say, so this is your scan chains. This is your scan chains. As I told you earlier, this is what is present inside your design. And when you add a scan chain, it will get converted into these kind of flip-flops having additional this. But inside it, what is there present? So your D flip-flop will remain like this. Clock is there. Q is there. Q bar is there. Right. Some output, they will provide some output. Then actually there will be a mux. One is D input, another will be having some SI input, right? Here the select line will be SE and there will be like this, the structure is. This is nothing but the structure of these flip-flops. Right? So this is what is happening when we are inserting DFT, the scan chains, right? And how the scan chain is working, which mode the scan chain is working on, what is the clock, everything we are going to discuss in triple MC properly in detail, right? So I will stop the technical part here. Now in detail, everything from this was the introduction. Now in detail, everything will be covered in the regular clips. So if there is any question, you can ask me. Additionally, I would like to tell that about the class timings, about the when it is going to start and everything. Our admin team is going to get in touch with you about it. So other than that, if you have any other question, you can just ask me.
I have some doubt regarding the code structure. Can I ask?
Yeah.
Yeah, so
Yes,
the case
Thomas.
is, so I'm going to enroll for the synthesis and STA course actually. So, so we will have this theory session, then we'll have the practical lab sessions also, right?
Yes. Yes.
Both for like synthesis and STA.
Yes. So what all things
And
I have
yeah,
Mhm. What all things I have in the start, see, I'm showing that list only on the screen. What all things I've explained here, right? So it is going to have the theoretical explanation also, and then we are going to implement it on lab also.
okay, okay. So another thing is like in STA, we'll do the pre-STA and post-STA both.
VHDL courses.
No, no, the STA will do the pre and post, both the STA will cover.
Yes, STA, like during the PNR also we are going to also cover prime time during the sign post. Yes.
Okay, okay, sure, sure, sure.
Any other question?
So this is the syllabus you're showing for the
Yes.
STA and synthesis, right?
Yes.
Okay, thank you.
Mostly the like as it will be advanced course, like we try not to go in very basic fundamentals because it's uh, expected that you know the flow, PNR flow, and what happens in what. We try to do all these experiments and analysis, like one or two step ahead. It is like that. So we'll be doing like lot of experiments on labs. Yes.
Yes, sure. I'm looking for the same. Actually, I'm working professional, so I just want to like improve my skills on STA. So that is my main concern. Synthesis I'm doing. Yeah,
Yeah, STA we are doing here. So,
sure. Thanks.
any other question? If you have. Fine then. I'll stop the session over here. Rest of the thing you can about the class timings, everything you can just connect with the admin team, and they are going to get in touch with you about it. Thank you, everyone. Then bye.